This week is a big one. We're going to cover a lot of content, chapters 3 and 4. I'm going to be moving pretty quickly through this video, but if you guys have any questions, please feel free. In section 3.1, we're going to calculate the formula masses for different compounds, and then we're going to talk about what a mole is and how that relates to Avogadro's. The first formula mass. The formula mass of substances is the sum of the average atomic masses of all the atoms in the substance's formula. So we take our molecule here, or our compound, okay? We look up the masses in the periodic table, and we multiply by how many of these different atoms we have, and then we add them all together in order to get the mass of that entire unit. So in this case, we have 1 carbon, 1, 2, 3 chlorines, and 1 hydrogen, okay? So we multiply carbon by 1, we multiply hydrogen by 1, we multiply the chlorine by 3, we get these values in AMU. If we add them together, we see that we wind up with 119.37 AMU for our chloroform molecule. Here are a couple more examples. We can see that it can get pretty complicated, but the formula is always the same. We count up our number of carbons, hydrogens, oxygens in this case. We multiply them by how many we have. Look up their atomic masses, we add them together, and get a molecular mass. Okay? It is important to note that the term molecular mass only applies to covalent compounds, covalently bonded compounds, whereas formula mass is the exact same value, but that applies to both ionic and covalent formed things. And the reason for that is because ionic substances, they're not discrete molecules, okay? They are cations and anions that are being combined in specific ratios to create a pattern, like a lattice structure that's going to make up the bulk that we material that we see in our world in the macroscopic level. Okay, so let's look at an example so you can see what I mean. So here we have sodium chloride. This is packed in this cubic sort of structure. So you could imagine this cube going on and on in every single direction to make up the sodium chloride that you see at your table. But the smallest repeating unit is always 1 sodium atom and 1 chlorine atom combined together. So our formula mass for sodium chloride is just going to be that 1 sodium and that 1 chlorine. We'll multiply those by their average atomic mass, add them together, and we get 58.44. It doesn't always have to be so clean. Here you can see aluminum sulfate has a very complex structure, but still there is a base repeating unit, certain proportion of the elements. And if we go to that proportion, you'll see that there are 2 aluminums for every 3 sulfurs, for every 12 oxygens, okay? We multiply them by their atomic masses together, get a mass of 342.14 AM. The mole. So the mole is an amount unit, similar to how a pair means 2, or a dozen means 12, or a gross is 144. The mole is just a number of things. Okay? And what that number is defined as is the number of atoms that are contained within a 12-gram sample of pure carbon 12. Seems like a little bit of a weird definition, but we'll see later why that behooves us to define it that way. The question is, how much is a mole? A mole is a lot of things, okay? It is 6.02214179 times 10 to the 23rd things, okay? A whole bunch of them. This number is known as Avogadro's number. You'll see it abbreviated with a capital N and a little a, and usually we just truncate it to be 6.022 into the 23rd. Why is this useful? Well, first let's take a look at the moles of different things. So if we look here, you can see that each one of these contains a mole of atoms. Each one of them weighs a different amount. That's because each individual atom weighs a different amount. Okay? But we can figure out how many atoms are in each one of these samples simply by weighing them, because we have defined the mole weight. The molar mass of an element. So this is where our definition really helps us a lot, okay? But it's a little tricky to figure out. The molar mass of an element is the mass in grams of 1 mole of that substance, a property expressed in units of grams per mole. So now we have a molar mass, units of grams per mole. We can interrelate mass and moles. This value is numerically equivalent. It is the same number as the atomic or formula mass of an AMU. So a single carbon-12 atom has a mass of 12 AMU, but a mole of those atoms has a mass of 12 grams. Okay, so we can convert between AMU and grams per mole. They are the same number. Just pick whatever unit we want to put on that number is convenient for the calculation that we're going to do. Here's another example of some moles of stuff. You can see that sometimes it's quite a bit if we have a very light or a very heavy compound. All right. Here you can just see a table that illustrates what I'm talking about. So carbon is 12.001 AMU, but also 12.01 grams for every mole. How many atoms are in that mole? 6.022 times 10 to the 23rd. These values are going to be different for each one of the elements. They'll be different for each of the compounds. So let's do some calculations that are going to relate the mass, moles, and Avogadro's number. Take a look at these. All right, so according to nutritional guidelines from the U.S. Department of Agriculture, estimated average requirement for dietary potassium is 4.7 grams. You're supposed to get 4.7 grams of potassium. What is the estimated average requirement of potassium in moles? So how many moles are in that 4.7 grams? So we start off with 4.7 grams from the problem, okay? We need to, we go and look up potassium in the periodic table. We see that that is 39.1 AMU. We know that AMUs are the same as grams per mole. How do we use that conversion factor? Well, we think about what our units there are that we want. I have grams, so I need to put grams into the denominator here so that it cancels. That leaves 1 mole in the numerator, and I see that it's 0.12 moles of potassium. Let's go from moles back to mass, okay? So a liter of air contains 9.2 times 10 to the negative 4 moles of argon. What is the mass of argon in a liter of air? So this time I'm starting off with moles. I need to put that 1 mole in the denominator here. I look up the atomic mass of argon. I see that that's 39.95. I put that up here in grams. Cancel my moles, and I see that many moles of argon weighs 0.037 grams. Okay, so when you're going to the number of atoms, you may be tempted to try and go straight from mass to the number of atoms. You think that that's possible? It is not. You have to do this in 2 steps. First, converting the mass to moles, and then converting those moles to the number of atoms. And we can kind of string those together. We don't actually have to calculate the number of moles and have a value for that. We can put them all together in order to get the atoms of carbon. So we start off with the 24 grams of copper in our problem up here. We divide that by the atomic mass of copper that we looked up, okay? So we're using the molar mass here. 63.546 grams of copper for every 1 mole. Now I have units of mole. Now I multiply that by the other conversion factor we have. We know that there's 6.022 times 10 to the 23rd atoms of copper in every mole of copper that I have. Okay, canceling my moles here, and I see that that sample of copper is 2.27 times 10 to the 23rd copper. All right, how many moles are there in a 28.35 gram sample of glycine? Okay, so in this case, before we had just elements, single atoms, now we actually have to figure out the formula mass of glycine first before we can figure out how many moles there are. We're combining two things together. So here's our glycine. There are 2 carbons, 5 hydrogens, 2 oxygens, and 1 nitrogen. We multiply each one of those by a molar mass here. Again, we're looking those up in the periodic table. We get values for each one. We add them together. We see that 1 mole of glycine weighs 75.07 grams. Take the amount of glycine we had from the problem. We divide that by that 75.07 grams. We get moles up here in the numerator. We get that mass of glycine, 0.378 moles. Okay, let's make this even a little bit more complicated. This time we have a packet of artificial sweetener. It contains 40 milligrams of saccharin, which has the structural formula. You can see it there. Given that saccharin has a molar mass of 183.18 grams per mole, how many saccharin molecules are in a 40 milligram sample, or 40 milligram sample? So that's pretty straightforward. The second question is, how many carbon atoms are in that same sample? So first we need to figure out how many of these guys we have in that 40 milligram sample, and then we need to figure out how many carbon atoms that is. We can see that there's 7 carbon atoms, 1, 2, 3, 4, 5, 6, 7, and for every one of these. So we're going to have to multiply the number of atoms of saccharin by 7 to get the number of carbon atoms. Go through that. The first step we're going to have to do is we're going to need to convert that 40 milligrams over to grams so that we have the same units between our molar mass in here, so we can cancel these grams. Okay, so 40 milligrams is 0.04 grams. Start there. We divide that by our molar mass. We now have units of moles, but we need to know how many molecules there are. We know that there are 6.022 times 10 to the 23rd molecules for every 1 mole. We multiply by that. We know that there are 1.31 times 10 to the 20th saccharin molecule. Counted up earlier that there were 7 carbon atoms for every one of those saccharin molecules, so we'll multiply that value by 7. We get 9.17 times 10 to the 20th carbon atom. Section 3.2 learning objectives. We're going to compute the percent composition of a compound, and we're going to determine the empirical formula of a compound, and then we're going to talk about the difference between an empirical formula and the molecular compound. Percent composition. Percent composition is not that difficult, really. Basically, you're going to take the mass, in this case, of each different piece of the compound, okay? And you're going to divide that by the total mass of that. I have a 10 gram sample, 2.5 grams of it is hydrogen, 7.5 grams of it is carbon. Then I know 7.5 plus 2.5 is 10, so this whole sample is either hydrogen or carbon. I can figure out the percent of it that is hydrogen by mass. So 2.5 grams divided by the entirety of the mass of the entire compound. Multiply that by 100%, I get 25% of it is hydrogen. In this case, if I have 7.5 grams of carbon, divide that by the total mass, multiply that by 100%, I get 75% of it is carbon. 25% plus 75% is 100%. So I now know the entire percent composition of this compound. It doesn't actually have to be mass. Okay? The thing that you have to realize is that it could also be the formula mass units. Okay? It doesn't have to just be grams. In this case, if we have ammonia, then we know that ammonia has a formula mass of 17.03 AMU. Okay? The atomic mass of nitrogen is 14.018. If I divide that by the formula mass of the entire compound, multiply that by 100%, I see that on a mass basis, ammonia is 82.27% nitrogen. Over here, I have hydrogen. I have to realize that there are 3 of these, right? So I do 3 times the atomic mass of hydrogen. I divide that by the total mass of ammonia, and I multiply that by 100%, I get 17.76%. Now, since we've covered every element that's in this compound, these two should add to give me 100%. And if you do the math there, you'll see it comes out pretty close, right? A little bit of wiggle room there, but that is mostly due to the fact that these are average here, that we haven't used quite enough decimal places to make it perfect. All right. So, empirical formula. A compound's empirical formula can be determined from the masses of its constituent elements. So we have 3 steps. First, we'll convert the element masses to moles. Then we divide each number of moles by the smallest number of moles. And then, if necessary, we will multiply by an integer to get whole values. So let's take a look at an example, or our flow chart. So we start off with some masses. There could be many of these, but in this case we just have 2. We'll divide them both by the molar masses. Now we have a set of moles. We divide by the lowest number of moles. Okay, so that means that one of these is going to wind up to be 1 in this scenario because we're going to divide it by itself. I'll show you an example in a moment. We get a mole ratio, and then we're going to convert that to whole values. Might wind up with fraction. The compound is determined to contain 1.71 grams of carbon and 0.383 grams of hydrogen. First step here, we're going to convert mass of carbon to the moles of carbon and the mass of hydrogen to the moles of hydrogen we did before. Now, if we just took these values and used them as the subscript or formula, we can see that that's pretty silly. You can't have fractions of carbon atoms or fractions of hydrogen. We need these to be whole values. So what we're going to do is we're going to take the smallest of these values and we're going to divide both of them by that. To do that, we wind up dividing this by itself, so we're going to get 1. And when we divide this one, we get 3.9. And this is where students get a little confused. We're not going to get too hung up on the fact that this isn't perfectly 4. We're just going to use an approximation and we're going to call it 4. Really don't need to worry about that unless you get to something like 3.5 or something like that. And we'll see an example of that now. So sometimes we're going to go through these steps and we're not really going to get whole values immediately. So start off in this example with the masses of chlorine and masses of oxygen contained in a sample. We divide them by their by their atomic masses. We're going to get these mole values. We place them to our formula, do our division by the smallest value, and we wind up getting something that's like 7.5. So pretty much 3.5 here. Really don't know whether to round that up or down. So what we do in that case is we just multiply both values by whatever is going to clear our fraction. So in this case, if we multiply them both by 2, we get 1 times 2. Remember that there was an implied 1 here, okay, because 1.15 divided by 0.15 is 1. 1 times 2 here, 7.5 times 2. See that we can empirical form CO2 7. So by adding one additional step, we can get the empirical formula from the percent composition. And basically what we're going to assume is that we have a 100-gram sample in order to get the masses that we need to start with to determine our empirical formula. So let's look at an example of that. In this example, the bacterial fermentation of grain to produce ethanol forms a gas with a percent composition of 27.29% carbon and 72.71% oxygen. What is the empirical formula for this gas? So we're going to start off by assuming that we have 100 grams of gas. It actually doesn't matter how much we assume there is of the gas, but 100 grams is very convenient. Okay. So if we have 100 grams of gas, 27.29% of it is carbon, 27.29 grams of carbon in the gas. Similarly for the oxygen, you wind up with 72.71 grams of oxygen. From this point, figuring out the empirical formula is exactly like the steps we saw before. We'll figure out the moles of carbon and oxygen. We'll place them into our formula. We'll divide by the smallest value. This time it works out almost perfectly, the carbon dioxide. So the molecular formula, the empirical formula, is not necessarily representative of a molecule. It is going to represent the smallest repeating unit in that molecule. So when you have a complex molecule that doesn't repeat itself, the molecular formula will be the empirical formula, but sometimes you need to multiply by a value in order to get from the empirical formula to the molecular formula when there's a high level of symmetry in that molecular compound. Let me show you what I mean by that. So in this example, we know that a compound has an empirical formula of CH2O. The empirical formula mass is 30 AMU. But we know that the molecular mass of this compound is actually 100. So if I take that 180 AMU, divide it by the 30 AMU, I get that there are 6 formula units per molecule. So then what I can do is I can go through and get used to this representation here. You see these parentheses here with the 6 out in front. I'm going to multiply each one of the subscripts by that 6. Get C6, H12O6 is the basic formula for any kind of sugar, monosaccharide. And I know that the molecular formula for this compound is C6H12O6. Section 3.3, we're going to describe the fundamental properties of what a solution is. We're going to calculate some solution concentrations using molarity. We'll learn what molarity is, and then we'll figure out how to perform the calculations to do dilution. So far we've been dealing with pure substances, but in fact most of the world is actually made of mixtures, things mixing together. Here's an example of a mixture with coffee and sugar. Coffee is already a mixture of water and coffee grounds. And it has been extracted from that. We add sugar in there, it will dissolve, and it will become part of the mixture, form a solution. Solutions are when these mixtures are homogeneous. So every point, every little bit that you would pick out of this solution is going to have the same uniform composition as every other bit. And this is what chemists like. Okay, if I go to take a sample of some liquid out of a container, I don't want to be thinking, is this different than some other bit of that same container? I want the entire thing to be homogeneous and the same throughout. So I know what I'm getting every time I take a sample. Mixtures, solutions are everywhere. Distilled white vinegar, for instance, is only 5% acetic acid, whereas the rest of it is actually water. So solutions consist of two components. You have your solvent. The solvent is the component that is in higher concentration. So there's more solvent than there is anything else. In our example before, the solvent is going to be your water. Then you have your solute. This is the component that is present at much lower concentrations than the solvent. In the previous example, the solute would be the acetic acid. And when we have a solution where the solvent is water, we often call this an aqueous solution. See that later. So molarity. So this is probably the unit that's most used in chemistry, and the reason for that being, we often want to know how many moles we're delivering, how many moles we're mixing with something else, and I want to be able to do that by measuring out specific volumes. So we need a unit that's going to relate the moles to the volume, and that's exactly what molarity is. So molarity is defined as the moles of solute divided by the liters of solution. So that's solution being the solute-solvent combination, not say the liters of solvent, but solution. Here's our example. A 355 milliliter soft drink sample contains 0.133 moles of sucrose, that's sugar. What is the molar concentration of sucrose in the beverage? So, given moles, I'm going to put the moles in the numerator, and I need to, my solution here is the soft drink. I need that in liters. I'll have to make a conversion down here. And what I wind up getting is that this is a 0.375 molar solution of sugar in our soft drink. So dilution is the typical way that chemists are going to prepare different solutions at different concentrations. It's not only convenient, but it has some other benefits that I'm discussing a little bit more now. But typically what happens is you have a concentrated stock solution, carefully prepared, exactly its concentration, and you can dilute down from that to get specific concentrations. So how do we handle the math to know how much of this sample to take out and what to dilute it up to get specific? The way we're going to do that is we start off with the definition of moles from this concentration. So if molarity is moles per liter, I take molarity, multiply it by the volume in liters, I'm going to get moles. But when you dilute something, so this is moles of the solute. So when you dilute something, though, you didn't change the solute concentration. You didn't change the number of moles of solute. You only changed the number of moles of solvent. Okay? So that means that the number of moles of solute initially in our stock concentration is going to be the concentration of that stock solution times the volume that we have of it, that we took from it. And the number of moles that we're going to wind up with in our diluted sample is going to be the concentration of that diluted sample times its volume, the volume that we diluted to. Okay? So these two equal each other. And if we set them equal to each other, we see that that what we wind up with is that the initial concentration of our stock solution multiplied by the volume that we withdrew from that stock solution to dilute is going to be equal to the concentration of our diluted solution we make multiplied by the volume, how much of that solution we make. Okay? This can actually be extended to other concentration units. So it's in general true that you can do this with any concentration unit. We'll talk about some of the other ones later. But C1V1 is always going to equal C2. Let's go through an example. So we start off with 0.850 liters of our 5 molar copper nitrate solution. We take that amount of this copper nitrate solution and we dilute that up to 1.8. Okay? What is the molarity of the diluted solution? So C1 in this case is our initial concentration, 5 molar, 5.00 molar. V1 is how much of that we withdrew, going to be our 0.850 liters. C2 is what they're asking us for. This is the concentration of the diluted solution. And V2 is the volume that we diluted up to. It's going to be our 1.80 liters. Solving for C2, we get this expression here. Plugging in our values, we wind up with this here. You can see that liters are going to cancel, and we're going to have units of molarity in the end. This number, 2.36, is less than our stock solution, which makes sense. The concentration must always go down for diluting. So in section 3.4, we're going to talk about some other concentration units. The first one is going to be mass percent. You'll see this a lot on a lot of consumer items because it's very convenient to weigh the solutes and the resulting solution. And so our mass percent is going to be the mass of the solute divided by the mass of the solution times 100%. You'll see that we typically are going to write this with the percent symbol followed by mass to indicate that this particular percentage is based on mass. Here's an example of where you're going to see that. Most household bleaches have an active ingredient of sodium hypochlorite, and that bleach is going to be between 5 and 10% sodium hypochlorite by mass. The next one is very similar, only this time we're going to do it by volume. So you might measure out the volume of a solute and divide that by the volume of the solution, multiply that by 100%, and get your percent by volume. The last one is one that I typically don't like to use because we're actually mixing different units here. You can see here that we can match these units and wind up with a unitless value. Multiplying that by 100% makes it a true percentage. But that's not true for mass volume. So here we're going to have different units. And so it's very important that when you look and recognize mass volume, that you always look for this percent mass divided by volume, M divided by V. And typically what this is going to indicate, because there's no other units given, is you're going to think, okay, if it's 0.9% mass by volume, that means that there's 0.9 grams of solute for every 100 milliliter solution. So 0.9% M over V is going to be 0.9 grams per 100 ml. You will see these mass volume values out there quite a bit. Probably the most common way that I see it is when they're talking about various blood levels. Very common to see this milligrams per deciliter value. ppm and ppb will make sense sometimes. These are pretty much the same as percent by mass, only, in this case, instead of multiplying by 100%, we're going to multiply by 10 to the 6 or a million for ppm, and we're going to multiply by 10 to the 9 or a billion for ppb. The reason that we do this is because these values are very, 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 very small, and we want to represent them in a way that is convenient so we don't have to write numbers small. So we just come up with a very, very small unit. When do we use ppm and ppb? You'll see it a lot with water samples or with air samples, anywhere where a very small amount of contaminant may have a very large effect. So in chapter 4, we're going to start talking about how we're going to use the tools we have so far to actually describe reaction. Start with one thing, and we're going to talk about how we write these, and then talk about how we go about balance. So a balanced chemical reaction uses symbolism to represent both the identities and the relative quantity of substances. So first we identify what our reactants are going to be, the things that are undergoing the reaction. Then we're going to identify what the products are going to be. What is it that we're making? We will separate out the reactants on the left-hand side of the equation with a plus symbol, and we'll separate out the products on the right-hand side with plus symbols. And we will draw an arrow going from the reactants on the left to the products. The relative numbers of these reactants and products are going to be represented by coefficients, and where we don't see a coefficient, we're going to assume that that is. So let's look at an example here. Here we have a carbon with 4 hydrogens attached to it to make a methane molecule. See that we wrote that C4, where the 4 hydrogens are represented by superscript. Here we have oxygen atoms containing 2 oxygen atoms. Okay, you can see that the 2 oxygen atoms are represented by the subscript 2, but because we have 2 of them, it gets a coefficient of 2 as well, for a total of 2 times 2, 4. Our products over here are going to be CO2 and 2 water molecules. We can scale this up, but we're always going to have the same ratios. There's still always going to be 2 oxygen atoms for every methane, always going to produce 2 water molecules for every CO2. So the chemical equation we just saw was balanced. That means that it had equal numbers of atoms of each element present on both the reactant and the product sides. That's important. That there's the law of conservation of mass. We can't create atoms, and we can't just arbitrarily get rid of them either. It is common practice when we're writing out these equations to use the smallest possible whole number coefficients in a chemical reaction. That if you can divide all the coefficients evenly by some value, you should do so. Get the smallest possible values. These coefficients represent the relative numbers of reactants and products, and therefore may be correctly interpreted as ratios. So you have one thing to another. And we saw in our previous example that with methane and oxygen, you have a 1 to 2 ratio. Requires 2 oxygen atoms or oxygen molecules to every 1 methane molecule, and that you're going to get out 1 carbon dioxide for 2 waters. This is important to be able to balance reactions. For instance, one big example is the fuel used for rockets. They have to be carefully balanced in order to get the appropriate amount of thrust. And you also want to make sure that you're actually able to burn all of the fuel accidents so that you're not left with leftovers when you shoot it off into space. So if an element appears in more than one formula on a given side of the equation, the number of atoms represented in each must be computed and then added together. So we need to figure out the atoms of each element. That's what we're balancing on each side of the action. So let's look at an example of that. In our previous one, where we had methane plus oxygen, the number, we have carbon, hydrogen, and oxygen. So on the reactant side, we have 1 carbon from methane, we have 4 hydrogens on methane, we have 2 times 2, 4 oxygens, and we get 1, 4, and 4. On the product side, we also have 1 carbon on the CO2, 4 oxygens, 1, 2, and 2 times 1, that's implied here, 4. And we have 4 hydrogens, that's this 2 times this subscript right here, 4 hydrogens. So every single one balances out. Let's look at one that doesn't. So in this case, if we look at the reactants, we have 1 times 2, 2 hydrogens on this water molecule, and only 1 oxygen on that water molecule. On the product side, this side, we have the 2 hydrogens, and we have 2 oxygens. So we can see that our oxygens are not balanced. The reactant side does not equal the product side in there. To achieve balance, the coefficients are what we're going to change. The coefficients of each of the molecules. We're not going to change the subscript. Okay? So how are we going to go about balancing this guy? We're going to first start off by putting a 2 in front of water molecules, because then we're going to get balance for the oxygen, okay? But that's going to unbalance our hydrogen at that point. How can we balance the hydrogens? Well, we have hydrogen all alone here, so that's why it was convenient to first start with our mixed species here, because we can just multiply this by whatever we want, multiply that by 2, and now you can see that it's a balanced equation with 4 hydrogens on each side, 2 oxygens on each side. This process is called balancing through inspection. Really kind of have to practice at this to be able to do it well. I have lots of examples in the homework. I suggest you check it out, and if you guys have any problems, feel free to contact me. One other method for doing this is to input a fraction where it makes sense. So as you were going along balancing this one, you said, wow, man, I mean, like what I really need is 7 oxygen atoms on the side. So if I multiply this coefficient by 7 halves, then I'll get those 7 oxygen. Okay? And that's perfectly fine. All we'll do is just multiply each coefficient by this denominator in order to clear the fraction. And we wind up getting our final balance reaction down here. So oftentimes we're going to add other things into the reactions in order to indicate various different things. So you're often going to see things that indicate, for instance, the physical. So often we're going to see things written in the reaction to indicate something about the process as it moves forward. One of the most common things is to indicate the physical state of reactants. So for instance, here we can see that each of these sodiums are a solid. We're using liquid water, that's producing sodium hydroxide in an aqueous mixture. So it's a water-based solution, all right, and that it's producing hydrogen as a gas. A lot of other times we may indicate something about the conditions by putting something over or under the arrow. Sometimes there'll be different reagents or catalysts listed underneath it. Common one you'll see is this delta here, or delta H, indicating that was heated or stirred. Energy was added to the reaction for it to take place. Many chemical reactions take place in aqueous media, and when there are ions, ionic compounds involved, we have choices about how we're going to write it. First one being the molecular equation, which looks very similar to the type of reactions that we've seen so far. We have all the compounds written out with their states next to them. But what's happening here is we're not explicitly writing out different ions that are participating. When we do that, what we'll see is that when the ions are in the aqueous medium, they actually dissociate. They break up into their ions, and then they're surrounded by the water molecules, which are able to stabilize those solutions. So calcium chloride will actually break down into one calcium 2 plus ion and two chlorine minus ions, so on and so forth throughout the whole thing, or other compounds. So it's really more realistic to represent these as dissociated ions. And so if we were to take our molecular formula, just break up each one of those compounds into ions, we wind up with what is called the complete ionic equation. And in the complete ionic equation, you can see that there exists kind of guys that didn't really do anything. So here we have calcium 2 plus, and over here we also have calcium 2 plus. Nothing really changed about that. And you have two nitrates here, and over here we have two nitrates. However, that's not true for all of them, right? So like here are silver and chlorides combined together to form a solid. So in order to represent only the changes that happen, we introduce the net ionic equation. And in this scenario, we're going to get rid of those guys that didn't participate in the reaction. They're called our spectator ions. And we're instead only going to focus in on the guys that change between. So what was a really long equation will simplify down to just silver combining with the chloride to form silver chloride. In section 4.2, we're going to define common types of chemical reactions. We're going to identify acids and bases. We're going to predict the solubility of common inorganic compounds by using the solubility rules. And then we'll compute the oxidation states for elements of compound. So precipitation. Precipitation is a process where you start off typically with ionic compounds in aqueous medium, and they will combine in such a way that a solid is formed. So in this case, we're forming, example from before, we're forming silver chloride. Sometimes these are known as double displacement reactions. Notice the chloride switch places with the nitrate to form sodium nitrate, and the chloride combined with the silver to form silver chloride. So they're kind of switching their anion in this case. What is solubility? So solubility, the solubility of a substance is specific to the conditions and the solvent that it's in, and maximum amount of that solute that you can fit into that liquid, that solvent. Okay. Substances where you can fit quite a bit of that solute into the solvent are called soluble. Substances where you solutes where you can't really fit much into a solvent are called insoluble. And if you fit too much of the solute into a solvent, what's going to happen eventually is a precipitate's going to form. Some solid solute is going to start to fall out. And you guys have surely seen this when maybe like some cleaner or something evaporates and it leaves behind like a solid residue. What happened is the solvent kept evaporating away, concentrating down that solute until eventually it formed into a solid. There are some very set rules for how solubility works. That kind of gives you a general idea of whether or not something is soluble or not soluble. We're actually going to be going over that in the lab. I need you guys to read that laboratory PDF to kind of better understand when something's soluble or when it's not. So if we look at an example here, we start off with this molecular equation here. And first thing we're going to notice is going to be the conditions. So we wind up with this solid here for our lead iodide. That means that this guy is going to be our precipitate. If we move to the net ionic equation, so this is our precipitate, we only have to be worried about the ions that form that precipitate. So only be looking at the lead ions, iodine ions. The rest of these guys over here, the potassium and the nitrate, those are just going to be our spectator ion. Here's a picture of this actual lead iodide forming those two compounds together. So here's another example, and again, we're just going to identify which one is the solid. That's going to be our precipitate, okay? And we're going to only focus on the silver and chloride that form that precipitate. We're making our net ionic equation. Acid-base reaction. So an acid-base reaction is one in which a hydrogen ion, H+, that is called also just a proton because it is just a single proton at that point, right? Is transferred from one chemical species to another. An acid is a substance that will dissolve in water to yield hydronium ions. So acids are going to give off protons, which will then react with water to form these hydronium ions. So an example of strong acids are ones where it very readily will give up that H+ ion. So a large portion of HCl, when placed into water, will give up that proton. You're going to get almost complete conversion over here to hydronium ions and chloride ions. Here's an example of various strong acids. You can see most of the acid halides. Halides will form acids, and many of the polyatomic will also form very strong acids. So weak acids will only partially give up their hydrogen ion. They're not typically going to all do it. So some portion of these molecules will give up the hydrogen ion, some will not. And in a general trend, many of these are going to be your organic acids, where they're based on carbon, oxygen, and so an example we've already seen is the acetic acid from the vinegar. This is a weak acid. Only about 1% the acetic acid that you're going to put into the water is actually going to dissociate out into that water sample. A base is a substance that will dissolve in water to yield hydroxide ion. Okay? This is one definition for bases. The most common bases are ionic compounds composed of alkali or alkaline earth metal cations combined with hydroxide ions. So in this example, we have sodium hydroxide, potassium hydroxide, calcium hydroxide, barium hydroxide. These bases, along with their hydroxides, completely dissociate in water, so that means that they are the strong bases. So in this example here, if we add sodium hydroxide solid to water, we're going to get almost complete dissociation into sodium ions, hydroxide. Just like acids, not all bases are strong bases. Some of them are weak bases. where only a relatively small amount of base is going to dissociate out when added to water. Ammonia is a good example of this. And still some things can be what they call amphoprotic. This means that it's capable of acting both as a base and as an acid. Water, for example, can give off a proton, or it may give off a hydroxide ion, depending on the conditions that it's placed in. A neutralization reaction, a specific type of acid-base reaction, and the reactants are an acid and a base. This is always going to result in producing a salt, that's a metal combined with a nonmetal, and water. Here's our example where we add magnesium hydroxide to HCl. We form magnesium chloride, magnesium being our metal, chloride being our nonmetal, form two water molecules as a result. Redox reactions. So redox is an oxidation reduction reaction. What's going to happen during a redox reaction is we're going to have a transfer of electrons from one of the reactant species to the other. Okay? So in this example here, sodium is going to give up an electron to the chlorine and form Cl- over here and a positive sodium ion here. That positive ion and the negative ion are going to combine together to form sodium chloride. So to view this, it is often helpful to split the reactions into what they call half reactions. So first we imagine that we have two sodium atoms that are neutral. Those go to yield two sodium ions plus two electrons. Then we imagine that we have our chlorine gas. We're going to add two electrons to it. It's going to form two chloride ions. To help kind of remember whether it is oxidation or reduction, whether one is losing electrons or gaining electrons, I like to think about the electron oil rig. So oxidation is loss. In our example before, the sodium lost electrons, so it got oxidized. Okay, and reduction is gain of electrons. So chloride gained electrons, it was reduced. So you can also talk about this kind of in the reverse, right? So if sodium is regularly oxidized, then it can be used as a reducing agent. You could add it to something else and it will reduce that other thing because it wants to be oxidized. Similarly, you could think of the reverse for chlorine. It functions as an oxidizing agent, and add it to other things, it will get reduced and it will oxidize those other things.
So the oxidation number of an element in a compound is the charge its atoms would possess if the compound was ionic. So we have a couple of rules for this. The first one for assigning oxidation numbers is that the oxidation number of a monotonic, a single atom ion, is equal to the ion's charge. So it's only compounds where we have to figure out anything particularly tricky about what the oxidation number is. The second rule is that the sum of the oxidation numbers for all atoms in a molecule or polyatomic ion equals the charge on the molecule or ion. Okay, so a neutral molecule, all the oxidation numbers are going to add up to be 0. If the overall molecule has a +1 charge, all the oxidation numbers will add up to be +1. Using that information and a few rules of thumb, we can start to figure out what the oxidation number is in our compounds. So the first thing that we want to do is have a few that we can easily identify. So hydrogen, when it is combined with a nonmetal, it's going to have a +1 charge. When it's combined with a metal, it's going to have a -1 charge. Oxygen, in almost every single case, is going to be a -2. And the halogens are almost always going to be a -1. So let's see if we do a couple examples, if we can identify some of the oxidation states. So in this guy, we have hydrogen. He's bound to sulfur, which is a non-metal. So we're going to expect that this hydrogen has a +1 charge. There's 2 of them, as indicated by this subscript. So for the entire hydrogens, we get a +2 charge. But the overall molecule is neutral, so it needs to be 0. So to balance the hydrogens +2, we need sulfur to be at a -2, which it really makes sense because sulfur is right beneath oxygen on the periodic table, and we already knew that oxygen was going to be a -2 charge. So here's another example. We have a free polyatomic here. This is going to be sulfite. And what we're going to do is we're going to go to one of the ones that we know. So we know oxygen is a -2. We have 3 of them, as indicated by this subscript right here. So 3 times -2 is going to be -6. So to give the overall molecule its charge of -2, we need to balance out the -6 from the oxygens, which means that we need sulfur here to be in a +4 state. -6 plus 4 gives us the overall charge of -2. And our next one here, we need to first identify what are our moving pieces inside of this guy here. So we have our polyatomic sulfate here. If we recognize that as being sulfate, we can look it up in the table that we provided in the last chapter, and we'll know that sulfate is a -2 charge overall. It's bound to 2 sodium atoms, which, as we saw in the last chapter, typically have a +1 charge. So we know pretty certainly that sodium is a +1 here. Now, if this sulfate is a -2 charge, and we get 4 times 4 oxygens, and that's giving us -8, then we're going to need sulfur to be in a +6 state in order to balance out all of our charges. Now let's look at some special examples of redox reaction. One example is the combustion reaction. This is where we're going to have some sort of reductant, also called fuel, that we're going to mix with an oxygen, which is often either elemental oxygen or a compound containing a lot of oxygen. This is going to react really vigorously. It's going to release heat, light, flame, and typically gases. So one of the reactions that we have here is the solid rocket fuel, where we're mixing aluminum metal with ammonium perchlorate. That's creating this aluminum oxide, aluminum chloride, and possibly even, and very importantly, it's releasing water gas and nitrogen gas. We're releasing a lot of gas here. This is what's causing that hot gas escaping, is what's causing the propulsion that's pushing the rocket forward. Single displacement. So we saw double displacement in the context of precipitation reactions, but there wasn't a transfer of electrons. In a single displacement, there will be, though. You can see that copper is neutral here, right? But then when it is combined with the nitrates on this side, nitrate having a -1 charge, you can see that there's 2 nitrates at -1, that's -2. Copper must be in a +2 state, so it moved from a neutral state to a +2 state in order to combine with the nitrate. Silver went from a +1 state here to a neutral state. So that means that electrons left copper and went to silver in this reaction. You can see that a lot of these redox reactions are spontaneous, such as the copper wire that's dunked into the silver nitrate solution. So balancing redox reactions can be very, very tricky. I did a problem in a whole video on how to do one of these in the homework, so I'd like for you guys to check that out as well. But we're going to go through the rules here, and then we're going to see about balancing one of these reactions. Rule number 1, we're going to write two individual half reactions, the oxidation and the reduction. We're going to balance all the elements except for the oxygen and the hydrogen. We'll balance the oxygens by adding H2O molecules. We'll balance the hydrogens by adding proton ions. We'll balance the charge by adding electrons. And if necessary, we'll multiply the half reaction coefficients by the smallest possible integers to yield equal numbers of electrons so that we can add them together. We'll then add the balanced half reactions together, and we'll remove the species that appear on both sides of the equations. If we are dealing in a basic media, so we're going to have hydroxide ions, we're going to have a few other steps. We're going to have to add hydroxide ions to both sides of the equation in numbers equal to the number of H+ ions. On both sides of the equation containing both H+ and OH- ions, combine these ions to yield water molecules, and then we'll simplify the equation by removing the redundant water molecules. And finally, regardless of what we do, we need to do a final check to see that the number of atoms are balanced in each of these reactions. So let's go through one together here. So we're going to write a balanced equation for the reaction between dichromate ion and iron 2 to yield iron 3 and chromium 3 in acidic solution. So we have our dichromate ion. We're going to add iron to it. We're going to yield out these guys here. We can already see that we don't have balance here, as there's not even any oxygen over here to balance out these oxygens here. So let's start by writing each of the half cells. So the iron went from an Fe2+ state to an Fe3+ state. And the chromate went from Cr2O7 2- to Cr3+. We will then balance the elements that are not oxygen or hydrogen. We have one iron here, we have another iron here, so we're good there. We have two chromium atoms here. We need to add a 2 over here so that we have 2 chromium atoms over there. Now we need to balance these oxygens that we have right here. So we have 7 oxygens on this side. We need to add water molecules until we can balance those. We need to add 7 water molecules over here. We now have the oxygens balanced, but we still have added this 7 times 2, 14 hydrogens on this side that we do not have on this side. Adding those 14 hydrogens to that side, we now have mass balance between the two sides. Now all we have to do is make sure that we are balancing our charges so that we can add the two reactions together. So now that we have mass balance for the elements on either side, we need to balance the charges. You can see on the left-hand side of this equation, we have a +2, just the one iron there. If we have plus 3 here, we need to add 1 electron with a negative charge. So we have plus 3 minus 1 is the same as the plus 2 over here. Here we can see that we have 2 times a plus 3, so this whole side is a plus 6. Over here we have negative 2 and 14 times 1, so 14 positive minus 2 gives this whole chunk right here a plus 12. To balance that with the plus 6 on this side, we need to add 6 electrons here. So we have this chunk at plus 12. Then we're going to minus 6 from that. So this whole chunk will be plus 6. And that equals the same as on the right side here. Finally, we're going to multiply the two half reactions so that the number of electrons in one reaction equals the number in the other. So we need to cancel these electrons just like we did the spectator ions before once we add the two reactions together. So we need there to be 6 electrons here and 6 electrons here. In order to do that, we'll have to multiply this top one by 6, every single one of the coefficients. Finally, we add them together. So everything on the left-hand side of both equations is going to go on the left-hand side of our new equation. Everything to the right of the arrow in both equations is going to go to the right in this one. And then finally, we are going to get rid of any of our spectator things that did not change in any way. In this case, the only things that did not change are going to be these 6 electrons. All the other guys did actually participate in the reaction, but sometimes you'll wind up with water molecules on this side and some on this side that need to be canceled. In our final check, we will add up all of the different elements and atoms on both sides to make sure that we have the exact same amount in both the reactants and the products. And then we'll check the charge on both sides to make sure that they are equal. In section 4.3, we're going to explain the concept of stoichiometry as it pertains to chemical reactions. That's exactly how do we manipulate the ratios of the coefficients. We will use the balance equations to derive stoichiometric factors. And then we're going to perform some stoichiometry calculations. So we're putting a lot of information in a small little form factor in a balanced chemical reaction. So we're telling you what the reactants are, we're telling you what the products are, and we're giving you some sense of the ratios, the quantitative relationships between them. This is what's known as the reaction stoichiometry. Balanced chemical equations are used in a similar fashion as recipes. From a balanced chemical equation, we can determine the amount of one reactant required to react with a given amount of another reactant, the amount of reactant needed to yield a given amount of product. The coefficients in a balanced equation are used to derive stoichiometric factors that permit computation of the desired quantity. So let's look at a little example of stoichiometry. I like this example. The general approach to using stoichiometric relationships is similar in concept to food preparation. So let's say that we have a recipe, and the recipe says that to make 8 pancakes, you need 1 cup of pancake mix, 3/4 cup of milk, and 1 egg. So we can write this recipe in chemistry speak as 1 cup mix, 1 3/4 cup milk, and 1 egg yields 8 pancakes. But what if we actually wanted to make 24 pancakes? If we wanted to make 24 pancakes, well then we need to have our stoichiometric factor. That would be this guy right here. So if we want to know how many eggs we need, then we know that there's for every 1 egg we get 8 pancakes. We can multiply this through, cancel our pancakes units, and we know that we need 3 times as many 3 eggs to make 24 pancakes. So let's plug in our chemistry equation this time. This equation shows that ammonia molecules are produced from hydrogen molecules in a 2 to 3 ratio. Stoichiometric factors may be derived using any amount or number of units. So we can talk about there are 2 ammonia molecules for every 3 hydrogens. There is 2 dozen of ammonia molecules for every 3 dozen hydrogens. And there are 2 moles of ammonia molecules for every 3 moles of hydrogens. How many moles of I2 are required to react with 0.429 mole of aluminum according to the following equation? So for every 2 moles of aluminum plus 3 moles of I2, we're going to get 2 moles of aluminum iodide. So our stoichiometric factor here, if we're given the moles of aluminum from the problem, then we know that there are 3 moles required to react with every 2 moles of the aluminum. We get our conversion factor here, and we see that we need 0.644 moles of iodine in order to react. What mass of sodium hydroxide would be required to produce 16 grams of antacid milk of magnesia, magnesium hydroxide, by the following reaction? So we have magnesium chloride plus 2 moles of sodium hydroxide is going to go to magnesium hydroxide plus 2 moles of sodium chloride. So the first thing we need to do is figure out how many moles of magnesium hydroxide is this 16 grams. So we take our 16 grams, we divide that by the formula mass of magnesium hydroxide. We now have the moles of magnesium hydroxide. So we have our mass to moles through the molar mass. Now to go from the moles of that down to the moles of sodium hydroxide, we need that stoichiometric factor. If we go back to the equation, we see that for every 1 mole of magnesium hydroxide, it required 2 moles of the sodium hydroxide. Here's our stoichiometric factor. We got the 2 moles sodium hydroxides in the numerator because that's what the unit that we want. We want to know the moles of sodium hydroxide, and we want to cancel the moles of magnesium hydroxide down here, 2 to 1 ratio. We multiply that through. We're now in units of moles of sodium hydroxide. Finally, we want the mass of sodium hydroxide. In order to do that, we need to multiply by the molar mass of the sodium hydroxide. We wind up getting 22 grams of sodium hydroxide. There are a lot of these problems. They can be asked in a myriad of different ways. I really like this web from the book. Really kind of shows you, depending on where you are and what it is that you're being asked in the problem, what values you're going to want to use in order to make the conversions necessary to get the other value. I think you guys should really check this out, maybe print it out when you're doing the problems and take a look at it. Section 4.4 Learning Objectives, we're going to learn about the theoretical yield and limiting reagents. The relative amounts of reactants and products represented in a balanced chemical reaction are often referred to as stoichiometric amounts. All the exercises in the preceding module involve stoichiometric amounts of reactants. In more realistic situation, reactants are not present in the actual stoichiometric amounts. So let's go back to one of our food examples. Let's consider that you're making grilled cheese sandwiches. You need 1 slice of cheese and 2 slices of bread for every 1 sandwich. Provided with 28 slices of bread and 11 slices of cheese, one may prepare 11 sandwiches per the provided recipe. All the provided cheese would be used, and 6 slices of bread would be left over. See, so if we have 11 slices of cheese, we can only make 11 sandwiches. That's going to require 22 slices of bread. 28 minus 22, we have 6 slices of bread left over. The number of sandwiches prepared has been limited by the number of cheese slices. Cheese is the limiting reactant. The limiting reactant will always be entirely consumed, thus limiting the amount of product that may be generated. The bread slices have been provided in excess. Bread is the excess reactant. Now consider a chemical process. Imagine combining 3 moles of hydrogen and 2 moles of chlorine gas. One approach for determining the limiting reactant involves comparing the amount of product expected for the complete reaction of each reactant. The reactant yielding the lesser amount of product is the limiting reactant. So let's take a look at that. So if we have 3 moles of hydrogen, we're going to produce 2 moles of HCl for every 1 mole of hydrogen. That would be 6 moles of HCl. If we have 2 moles of chlorine, we'd produce 2 moles of HCl for every 1 mole of chlorine, and that would be a total of 4 moles of hydrochloric acid. So once we had made 4 moles of hydrochloric acid, we would have used up all of our chlorine. So in this case, chlorine is the limiting reactant, and hydrogen is the excess reactant. Here we can picture this actually happening, where we're mixing chlorine and hydrogen, and we have some leftover hydrogen. The amount of product that may be produced by a reaction as calculated per the stoichiometry of an appropriate balanced chemical reaction is called the theoretical yield of the reaction. The amount that we actually get, though, when we do the reaction is our actual yield. There's a lot of reasons that the actual yield will never reach the theoretical yield, including competing side reactions, incomplete reactions, and possibly just difficulty in actually collecting all of the product from our reaction. So our percent yield is basically how good we did. We're going to take the actual yield, what we actually got, we'll divide that by what we should have gotten, and we'll multiply that by 100% to give us our percent yield. It is important to note that your actual yield and your theoretical yield should have the same units. So upon reaction of 1.274 grams of copper sulfate with excess zinc metal, 0.392 grams copper metal was obtained according to the equation. Copper sulfate plus zinc metal goes to copper solid with zinc sulfate. So what was our percent yield? So we need to figure out if we had 1.274 grams of copper, how much copper sulfate, how much copper would we expect to be making? So if we start off with the copper sulfate we had, we'll figure out how many moles of copper sulfate that is. We know that there's a 1-to-1 ratio because there's no coefficients here. We'll assume there's a 1 here and a 1 here between the copper sulfate and the copper. And then we multiply by the atomic mass of copper, and we should have gotten 0.5072 grams of copper. Plugging in the actual yield that we got from the problem, we get 0.392 grams of copper divided by 0.5072 grams of copper times 100%. We got a 77.3% yield. Section 4.5 learning objectives. We're going to describe the fundamental aspects of titrations and gravimetric analysis, And then we'll perform some stoichiometric calculations using typical titration and gravimetric data. Quantitative analysis. This is to determine the amount or concentration of a substance in a sample. This is distinct from qualitative analysis, which tells us what is in the sample. We'll discuss two main types of quantitative analysis, titration and gravimetric analysis. Titration. Titration involves two solutions. The titrant, a solution containing a known concentration of one reactant, and the analyte, a solution containing a reactant of an unknown amount or concentration. Measuring the volume of titrant solution required for complete reaction with the analyte, the equivalence point of the titration allows calculation of the analyte concentration. How are we going to know when they've reacted completely with one another? We often use indicators. These are added to the analyte solution to impart a change in color at or very near the equivalence point of the titration. The volume of titrant actually measured is called the endpoint. The difference between the equivalence and endpoints should be negligible. And you do that by choosing the appropriate indicator. It's going to change near the actual equivalence point. The endpoint in a titration of a 50 milliliter sample of aqueous HCl was reached by the addition of 35.23 milliliters of 0.250 molar sodium hydroxide titrant. The reaction is, so we have a acid-base reaction here. We're adding acid to a base. We're producing a salt, sodium chloride, and water. They're asking us, what is the molarity of the HCl? So the first thing we need to do is figure out how many moles of sodium hydroxide reacted. We need to multiply this volume by this concentration. We need to have the appropriate units of liters here. Here's our flow chart. We're going to start off with the volume of sodium hydroxide. We're going to use the molar concentration to figure out the moles of sodium hydroxide. We'll then use the stoichiometric factor to figure out the moles of HCl. And finally, we'll use the volume of solution to figure out the concentration of HCl. So, we take 35.23 milliliters of sodium hydroxide. We use that conversion that I mentioned to get it into liters. We'll multiply that by that concentration. We have 8.81 times 10 to the negative 3 moles of sodium hydroxide. Next, we'll calculate the number of moles of HCl using stoichiometry. We get those moles of sodium hydroxide. We use our conversion factor of 1 to 1. And now we have our moles of HCl. Finally, we'll calculate the molarity of HCl. We take those moles of HCl and we divide it by the volume that it was contained in. It was a 50 milliliter sample. Do not forget to do your conversion here, because if this is molarity, it needs to be in liters down here. And we see that it was 0.176 molar HCl. Gravimetric analysis. This is where we're going to analyze things by weighing them. A type of analysis in which a sample is subjected to some treatment that causes a change in the physical state of the analyte that permits its separation from other components of the sample. Mass measurements of the sample, the isolated analyte, or some other component of the system, used along with known stoichiometry of compounds involved, permit calculation of the analyte concentration. Commonly, the analyte is separated by subjecting it to a precipitation reaction. So we precipitate out things that we want to analyze, and then we'll weigh them. Here we have an example. A 0.4550 gram solid mixture containing magnesium sulfate is dissolved in water and treated with an excess of barium nitrate. This results in the precipitation of 0.6168 grams of barium sulfate. So we're mixing magnesium sulfate, barium nitrate. We get out barium sulfate and magnesium nitrate. This is a double displacement reaction and a precipitation reaction. We can see that barium sulfate has been marked as the solid here, so we know that's our precipitate. What is the concentration, mass percent, of magnesium sulfate in the mixture? So we're going to start with the mass of barium sulfate. We will use its molar mass to figure out the moles of barium sulfate. I've hoped that you guys have noted that the first step in almost all of these problems is knowing the moles of the compounds that we have. We'll then use the stoichiometric factor to figure out the moles of calcium sulfate that we should have. Then we'll go back through the molar mass of the calcium sulfate, get the mass of calcium sulfate, and then we will divide by the sample mass to get the percent of the calcium sulfate. So let's start off here. From the problem, we know that we have 0.6168 grams of barium sulfate. We can calculate the formula mass of barium sulfate to get the moles of barium sulfate. We have our stoichiometric factor here, 1:1 between barium sulfate and magnesium sulfate. We now have the moles of magnesium sulfate. We multiply by its formula mass that we've calculated, and we get that our final value is going to be 0.3181 grams of magnesium sulfate. Using this result and the mass of the initial sample, we can calculate the percent composition. So we know that 0.3181 grams of the original sample was magnesium sulfate, but it was a 0.4550 gram sample. Some of this was inert material. So we take this, we divide it by that, we times that by 100%, and we see that it was 69.91% magnesium sulfate. Combustion analysis is when we burn things and then analyze the gases that come off in order to figure out the composition of the initial sample. The complete combustion of hydrocarbons, for example, will yield carbon dioxide and water vapor as the only products. The gaseous combustion products are swept through separate pre-weighed collection devices containing compounds that selectively absorb each product. The mass of the absorbed product can then be used in an appropriate stoichiometric calculation to derive the moles and mass of the relevant elements. Let's take a look at what that looks like. So we have sample here. We're hitting that with a lot of oxygen. It's in a super hot furnace. It burns, produces gases. H2O, water gets absorbed here. CO2 gets absorbed here. O2 and the other gases continue on. We can weigh these cells later to figure out how much water there was and how much CO2. So let's look at an example of this guy. Polyethylene is a hydrocarbon polymer used to produce food storage bags and many other flexible plastic items. A combustion analysis of a 0.00126 gram sample of polyethylene yields 0.00394 grams of CO2 and 0.00161 grams of water. So we know that this is a hydrocarbon, meaning it contains carbon, some amount of carbon, some amount of hydrogen. We're not sure what those proportions are yet. We're going to have an excess of O2, more than we need, and that's going to produce CO2 and H2O. What is the empirical formula of our polyethylene? So the first thing we need to do is figure out how many moles of these two we initially had. Here's our flow chart. We have the mass of CO2, the mass of H2O. We figure out the moles of these two values. We use the stoichiometric factor to figure out the moles of carbon, and then the mass of carbon. And then we can use our stoichiometric factor to figure out the moles of H2, the mass of H2. Then we start looking at the ratios between them, in order to get our empirical formulas in percent composition. So let's take a look at the calculations for that. We start off with our two masses. We divide each one of them by their formula masses to get the number of moles. And then we figure out how many moles of hydrogen there are, how many moles of carbon there are, based on how many atoms there are in each one of these molecules. And then we now have the moles of hydrogen and the moles of carbon. The empirical formula for the compound is then derived by identifying the smallest whole number multiples for these mole amounts. H to C mole ratio is. So just like we did before, we're going to divide by the smaller of these two values, and we see that there is a 2-to-1 carbon-hydrogen ratio. Plugging that in our original formula, we get CH2 for the empirical formula.